Now, this is absolutely amazing. How you've been looking at bacteria and how they move?
How bacteria swim. So ultimately, most bacteria swim, and they swim by this tiny rotary motor which they rotate very fast.
Let me
Whoa. Okay, yeah,
say that again.
Yeah, you're talking about they have some sort of propeller system.
Yes, yeah, exactly. It's rather than waving or swimming like a dolphin, it rotates like an outboard motor.
It's almost mechanical.
Yeah, I mean, it effectively is mechanical in that energy is converted into this rotation. So electrical energy, it's a tiny electrical motor that rotates the propeller and makes them swim.
How does it get made? Who makes it? Where's the factory?
Well, that's the most amazing part about it, is that it actually makes itself, it builds itself. So the components, there's about 100 proteins that make up this motor, and they somehow know how to get to the right place and build themselves. And it's got lots of complicated rings and dynamos and things like any other motor.
Okay, let me guess then. You are trying to replicate that.
That's one of the things we're trying to do, particularly trying to modify it so it can swim in different ways, but more really to show that we actually understand how this works and builds itself, because it's the building itself that's the bit that we can't really do ourselves as sort of man-made technology nowadays.
But if you could synthesize that, what are the applications?
Well, any sort of science fiction-esque thing where you might want to swim through your body and deliver, say, a drug, or maybe if you're a bad science fiction writer and you wanted to have evil cameras that could float around and surveil us, this type of machinery, understanding how we can build really small things, but in the next era. Currently we make them one brick at a time, but biology just throws all the bricks together and builds a marvelous machine. So we need to learn how to do that.
And this is sort of part of nanotechnology, where we're talking on a very, very sort of molecular scale, I guess, to deliver things into the body. Machinery, essentially, to perhaps fix things.
Yeah. So the way bacteria do it, it's not just to move. The machine itself is actually able to navigate bacteria to where their life would be better. So as it's powering it along, it can tell, oh, there's more food over here, or there's less food over here, and I should change direction. So it's more than just a propeller. It's a very sensitive propeller that's adaptive and able to navigate to a specific location. So if you can adapt that with medicine, then you can deliver it where it needs to be.
Wow.
Given.
So Karl, bacteria are obviously fascinating. Now there's also applications for spiders.
That's right, and the bacteria marry back in. So if you think about the spider thread, there are so many different types. There's the gossamer thread, which is a very thin, light one. They just spray it out, and they jump off the tree branch, and they get carried by the wind to the branch over there. And sailors have picked them up at sea, 20 kilometres out. So there's a thin gossamer thread, there's a stiff one thread for wrapping the cocoon for the babies, and then there's a really strong dragline thread, and that is actually about as strong, size for size, as high tensile steel. So we've been able to get steel and spiderweb silk about the same, but the scientists have actually taken it one stage further.
Well, let's get Matt to explain that then. Given the tensile strength that they make themselves.
Well, what this recent work shows is that miraculously, if you spray a vapor with a lot of little carbon nanotubes in it, then somehow this gets absorbed by the spiders and it makes the spider webs that they make much stronger.
So you simply just spray the spider.
It's astonishing. So you get the carbon nanotubes, you mix them up in water, you get your little kitchen whiz and go rah, 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 and then you get a little kitchen sprayer and go, hey, little huntsman spider, you know, the daddy long legs, squirt, 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 and some of them will incorporate these carbon nanotubes, and suddenly you've got a fibre that is stronger than the strongest known fibre that we humans can make. There's Kevlar, and then there's Kevlar 49 TM, which is the guide, the gold standard. These spiders can make something stronger than that, and we don't know how.
So, Matt, then is the aim to look at how the spiders do that and then perhaps, once again, synthesize it?
Well, spider silk has been of interest for generations because we know it's very strong, but it's also very flexible. But the problem's always been making enough of it. So it's hard to get hundreds or thousands of spiders to make enough to build a sail or a rug or anything.
Well, because they don't like living together necessarily, do
Exactly.
They eat each other. You end up with just one spider.
So one of the ways we've got to sort of overcome this is using modern bioengineering. We can get other animals to express spider silk and perhaps make a better effort that way.
So other animals? What, say, silkworm? Or?
So the first example that's a little bit crazy was to do it with goats. They managed to get goats expressing this silk protein out of their milk. So you'd effectively milk a goat, get a lot of milk with lots of spider silk protein in it, and then purify it down and spin it out. Now this didn't really work.
Without having to mate a goat with a spider, which would probably be fairly difficult.
Yeah.
So this is all done with sort of genetic engineering. We don't actually have to make spiders and goats fall in love and cohabit and make spider silk milk. But ultimately, that sort of wasn't really a goal because it's quite hard to milk goats in an industrial sense over time to build lots and lots of silk. So the latest way of doing it is actually using bacteria again. So we can again get bacteria to express this silk protein, and we can purify it and create the conditions to build silk threads. It's really a great biomaterial. It's kind of the greatest hope from biomaterials to apply to new things.
And the temperature range, it'll withstand anything from -40 to +220. So you could clean your clothes not by putting them in the washing machine, but just by running them quickly through a flame. Maybe that's pushing it a bit much.
I won't try that at home. Dr. Karl, Dr. Matt, thanks very much.
Dr.
Thank
Andrew.
you.